Hi everyone, welcome back to the 11th lecture of E635 Applied Linear Algebra. This is the second module. In the first module, we saw that when we have differential equations or difference equations, the problem is we may have coupled systems of equations, right? And those coupled systems of equations are indeed very difficult to solve. However, if they're decoupled, then they become absolutely simple. So a natural question that arose was, is it possible to, so given a system of equations, is it possible to make it decoupled? And we saw that if this matrix that we have, so x dot equals ax or xk plus 1 equals a times xk, if this matrix A admits n linearly independent eigenvectors, then it can be decoupled, right? In this module, we're going to ask this question. We're going to start investigating this question: that when can we predict that the matrix A will have n linearly independent eigenvectors? But before we do that, we have to formalize the notion of eigenvalue eigenvector, yeah, of a linear operator in general, not necessarily a matrix. Okay, so let us see what happens then. Yeah, right. So I have to share my screen. Right. So I had given this immediate attention problem. I hope you have attempted. This one I'm not going to do. This you will do yourself. But let me try and do this one for you. Yeah, this will be instructive for us. Okay. So what we are asking here is Q1 analog of Q2. That is, we have given an answer to Q2, a partial answer to Q2. What would be the analogous partial answer to Q1, right? So what does Q1 say? That okay, A is a square matrix with real entries. How can I diagonalize this by a matrix T so that T inverse AT is diagonal? This is the symbol for diagonal matrices, big lambda. So what T should I choose? So suppose V1 up to Vn are vectors in Rn such that this first of all is linearly independent, and A acting on Vi is equal to lambda I Vi. In that case, if I look at A times T, that is A times V1 V2 dot 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 up to Vn, then this is nothing but, well, A times V1 A times V2 dot 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 up to A times Vn. But well, this is, so they satisfy this equation, right? So this is lambda 1 times V1, lambda 2 times V2 dot 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 up to lambda n times Vn. So these are the columns. So these lambda 1s up to lambda 1 up to lambda n are such that they multiply these columns, right? So this, notice, that can be written as V1 V2 dot 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 up to Vn, once again the matrix. This now a column operation is done on it so that each column gets multiplied by the respective lambda value. So this is the diagonal matrix. We call it capital lambda, and we have already defined this to be capital T. So then the equation that we get out of here is that AT is equal to T times lambda, which then tells us that T inverse AT is equal to lambda. So you see, we get back the same thing as we have done before by the abstract idea of eigenvectors like this and representation of the linear operator in terms of that basis given by the eigenvectors, the n linearly independent eigenvectors. Yeah, the representation turns out to be diagonal. But then if we don't want to do that, we want to do everything in terms of matrices, then suppose A is a given square matrix n by n, and T is a matrix formed by taking linearly independent eigenvectors, n linearly independent eigenvectors. Linear independence guarantees that T is invertible. In that case, representation of the matrix A in this new basis, which is T inverse AT, that turns out to be diagonal. That is the Q1 analog of the partial answer to Q2 that we saw in the first module. But the question still remains that when do we have these linearly independent eigenvectors? I've been using this term eigenvectors without formally defining it. So let me do that first. So we now have the definition. Remember that we have promised that we're going to do things from more sophisticated abstract point of view. So I'm not going to use matrices here, but instead I'm going to use linear operators, the language of linear operators. So let phi be a linear operator from V2 itself, where V is a vector space over a field F, and dimension of the vector space V is n, which is finite. Yeah. Um, suppose V in V is a non-zero vector and lambda is a scalar from the field, such that phi's action on V is equal to lambda times V. Then V is called an eigenvector of phi corresponding to eigenvalue lambda. Yeah. Eigen in German means own, as we'll see later on, that these are special vectors because phi is such that it doesn't. So okay, in general, you see, if let's say this is my vector space and this is some vector, an operator would in general move this vector around, right? So when phi acts on it, it takes it to, so this is V, this is phi V. This is what in general happens. But for eigenvectors, they are special because the action of the operator on the vector just elongates or contracts this vector, doesn't make it rotate, doesn't make it move out of this span of V, right? That's why they are called eigen. They're special vectors. In some sense, the linear operator phi is kind of biased towards these vectors. Yeah. And eigenvalue is the corresponding eigenvalue, right? One more point to notice here is that V must necessarily be non-zero. Otherwise, you see, if you take zero vector, then phi 0 is 0, which is 0 times V, which means if I allow zero vectors, then every linear operator will have 0 for an eigenvector and 0 an eigenvalue, which is not interesting. Yeah, so therefore we want non-zero vectors, and as you can see that for the diagonalization purpose also we need linearly independent eigenvectors, right? So if I want linear independence, then I should better have non-zero vectors, otherwise the question of linear independence is meaningless. So therefore it is necessary to assume that V is non-zero. So whenever we say eigenvector, by default we have to assume that V is non-zero. Yeah, it's a non-zero vector. Sometimes we may not specifically mention that it's a non-zero eigenvector, because the moment I say eigenvector, it's understood that it has to be non-zero. Yeah, is that all right? So this is a eigenvector. Now the question is, how do we get these eigenvalues and eigenvectors, right? Notice that if I have this V and suppose I have an ordered basis, so suppose V has an ordered basis, say B, under which the linear operator phi is representation is given by a matrix A. Yeah? This A must belong to f n cross n. Yeah, is that all right? Now, if V is an eigenvector, yeah, then this implies phi acting on V is lambda times V, right? Which then means lambda identity minus phi, this linear operator, when this guy acts on V, this produces 0. However, this also means that lambda I minus phi, this operator's representation under B, when acts on the representation of the vector V under that basis, that must produce 0 in that basis, which is the 0 vector. This is the 0 vector of f to the n. Yeah, but now, so this is the same as saying lambda I minus the matrix A V B is equal to 0. In fact, all these are if and only if. So this implies, this is if and only if this vector V representation belongs to the kernel of this operator lambda I minus A. Yeah, this matrix lambda I minus A. So, and remember, this is, in order for this to be an eigenvector, this has to be a non-zero vector. Now, when would I be able to find out non-zero vectors in this kernel? If and only if lambda I minus A, so there exist non-zero vectors. So this is true if and only if there exist non-zero vectors in kernel of lambda I minus A, which is if and only if lambda I minus A is singular, which is if and only if determinant of lambda I minus A is equal to 0. Yeah. Now this allows us to define a polynomial which is determinant of Si minus A, where I take S to be a placeholder. It's a variable. I don't put any value to it. It's just some S symbol. This is going to be a polynomial. So this is going to be a polynomial in S. In fact, an nth degree polynomial. Degree of this polynomial is n. It's a monic polynomial. It's monic. That means it's the highest degree coefficient is 1. Yeah. So in order to get this, yeah, so from this definition, it follows that, determinant lambda I minus A equal to 0 if and only if lambda is a root of this polynomial. Right. So this chi as is the so-called characteristic polynomial of A. Yeah. Now notice something interesting. You see, right, and notice that this lambda I minus A is singular. That is, there exists a non-zero vector in this kernel if and only if lambda is a root of this chi as. Right. So let me write this thing also, that kernel lambda I minus A is not just 0 if and only if determinant lambda is 0, if and only if lambda is 0. So these are precisely the, so the roots of this polynomial are precisely the points, precisely the scalars at which lambda I minus a um, becomes singular, and therefore I can find non-zero vectors there, right? But then one might ask this question that, okay, this linear, so my starting point was this linear operator phi, right? And this linear operator phi may have various different matrices A based on these ordered bases. I choose a different order basis, I get a different matrix A, isn't it? So one matrix may give some characteristic polynomial, the other matrix may give a different characteristic polynomial. So which one do I believe in, right? It turns out that this is meaningless. I mean, this is not even required. The reason is that no matter what basis you choose, the characteristic polynomial that you get for that matrix, that remains always the same. Yeah, it depends only on the linear operator and not on its matrix represent, on its any particular matrix representation. I'll tell you why. So suppose B tilde is another ordered basis for the same vector space V, and let phi representation under B tilde is given by A tilde. Then we know, we have already seen before, even before midsem, we know that A tilde is nothing but some T inverse A T, right? Where T is that invertible matrix. Now notice what happens. Chi of A tilde S is determinant of Si minus A tilde, which is the same as determinant of Si minus T inverse AT. Note that this can be written as determinant of ST inverse identity T minus T inverse AT, which is the same as determinant of T inverse Si minus A into T. Now determinant has this nice property that if it's determinant of a product, it's the product of the determinants. So this is determinant T inverse, determinant Si minus A, and determinant T. And determinant of T inverse and determinant of T are reciprocals of each other, so they cancel out. This is the same as determinant of Si minus A, which happens to be characteristic polynomial of S. So you see, chi A tilde S is the same as chi AS, right? So this chi phi S then is defined to be chi AS or chi A tilde S, doesn't matter. Just take any basis, find out the matrix, do this determinant of Si minus A, that is the characteristic polynomial of the linear operator. This is the characteristic polynomial of the linear operator phi, right? So this is the deal. Now from this point onward, we are not going to distinguish as such between linear operator phi or a matrix A. So we're going to use just A for these operators. So we're going to say that, okay, so for us A is the one that we're going to deal with. Either you view this A as a linear operator from V2 itself. This is the abstract point of view, the one that we prefer. Or if you feel uncomfortable, you can view A as a matrix also, right? But we are going to use the same symbol A, okay, unless otherwise specified. All right. So I hope this idea is clear. Now we come to our original question that okay, we know that um, if A admits n being the dimension equal to the dimension of the vector space V. So if A admits n linearly independent eigenvectors, then A diagonalizes. Yeah, that means if you're viewing them as matrices, viewing A as a matrix, then there exists a matrix T whose columns are precisely these linearly independent eigenvectors. In that case, T inverse AT will be a diagonal matrix. Or if you are viewing A as a linear operator, then that means there exist these eigenvectors whose which if you choose these eigenvectors as a basis for as an ordered basis for the vector space V, then this linear operator under this ordered basis takes up the form of a diagonal matrix. In both cases, we say that A, the operator or the matrix, diagonalizes. The question is, when is this true? So the question, when do we have n linearly independent eigenvectors? So we're going to first see a partial answer to this question, and then we're going to see a little more general but still partial. No, we are going to look at, yeah, in fact, we're going to look at a complete answer to this question. First, we're going to look at a partial answer, and then we are going to look at a complete answer to this question. So first, the partial answer. Partial answer happens to be the fact that if A has n, where n is the dimension of the vector space, n distinct eigenvalues, then A admits n linearly independent eigenvectors. You understand, no? This is important. So if there are as many linearly independent, as many distinct eigenvalues as the dimension of the vector space, then there will be n linearly independent eigenvectors. But remember that this is a sufficient condition. This is not necessary. This is not the only situation where there will be n linearly independent eigenvectors. That is the general answer. That is the complete answer, which we'll see very soon. But now first we have to make sense of why is this true? Why, if there are n linearly, why if there are n distinct eigenvalues, then there will be n linearly independent eigenvectors guaranteed, right? So in order to understand what is the relation between the distinct eigenvalues and linear independence of eigenvectors, we have to first prove the following lemma. Let us try and do that. What is that lemma? Okay, so the situation is just like before. We have V over F, dimension of V is n, which is finite. A is a linear operator from V to itself. Yeah. Now let lambda 1 dot 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 up to lambda k in F be distinct be distinct and V1 up to Vk in V be such that lambda, okay, such that A Vi equals lambda I Vi, where I goes from 1 to 3 up to k. Then V1 up to Vk is linearly independent. Yeah, is that all right? Proof. The proof is going to work. The proof is done by induction. Yeah. So I'm going to do this formally. Proof by induction, base step by induction, of course, on the parameter k. The base step being being k equal to 1. Yeah, in that case, the set V1 is Li because these are eigenvectors, right? So these Vi's are non-zero because V1 by definition is non-zero, by assumption of the lemma is non-zero. We are dealing with eigenvectors, right? And I have already mentioned that eigenvalues are by default non-zero vectors. So V1 is non-zero, therefore it must be linearly independent. So when we have one single vector, if it is non-zero, it's linearly independent, right? So base step is done. Now the inductive step. So inductive step assumes, so we assume the truth of the statement for k. We have to show that the statement holds for k plus 1. Yeah. Now, so suppose suppose a linear combination, suppose a non-trivial linear combination of V1 up to Vk plus 1 goes to 0. That is alpha 1 V1 plus dot 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 up to alpha k plus 1 Vk plus 1 is equal to 0, right? Now, since this is a non-trivial linear combination, not all alpha i's are 0. So, some of them must be non-zero. We may assume without loss of generality, we may assume that alpha 1 is not equal to 0. Yeah. So, if alpha 1 is not equal to 0, then this implies V1 is in fact equal to some beta 1 V2. Actually, we may assume that that's easier to write down. Notation wise, it becomes easier. We may assume that alpha k plus 1 is not equal to 0. Right. So then this implies Vk plus 1 is equal to, because alpha k plus 1 is non-zero, I can just divide by alpha k plus 1 and write it like this. Yeah, which is the same as writing this to be equal to some beta 1 v1 plus dot 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 up to beta k v k. Yeah, okay. Now multiply by a, I mean make a act on them, on these things both sides. This is a acting on beta 1 v1 plus dot 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 up to beta k vk. This is the same as beta 1 a v1 plus dot 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 up to beta k a vk, right? But remember, these things satisfy that this is lambda k plus 1 vk plus 1. This is lambda 1 beta 1 v1 plus dot 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 up to lambda k beta k vk. Yeah, is that all right? Okay, but now I can also replace this vk plus 1 by this expression, which is the same as lambda k plus 1 beta 1 v1 plus dot 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 lambda k plus 1 beta k vk, and that is equal to lambda 1 beta 1 v1 plus dot 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 up to lambda k beta k vk. Taking everything on one side, we have, so notice carefully, what we have is beta 1 lambda k plus 1 minus lambda 1 into v1 plus dot 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 beta k lambda k plus 1 minus lambda k into vk. This is equal to 0. Yeah, but by assumption, this v1 up to vk, there are k number of vectors. So for k number of vectors, we have assumed that the statement is true. So that means by assumption, v1 up to vk is linearly independent. If v1 up to vk is linearly independent, then this implies beta 1 lambda k plus 1 minus lambda 1 is 0. Beta 2 lambda k plus 1 minus lambda 2 is 0. So on, beta k lambda k plus 1 minus lambda k is equal to 0. But these are distinct. So this is non-zero, this is non-zero, all these guys are non-zero. So this implies beta 1 must be 0, beta 2 must be 0, and so on up to beta k must be 0. Yeah, because all these are coming from the field, this is non-zero, so I can divide by this inverse, which means beta 1 must be 0. Yeah, so these numbers are 0, beta 1 up to beta k, which then implies vk plus 1, which is equal to beta 1 v1 plus dot 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 beta k vk. This is equal to 0 because these are linear combinations. Yeah, beta 1's these coefficients are 0, but there is a contradiction because these v's have been assumed to be non-zero. This is a contradiction. To beta vk plus 1 being non-zero, which then means that our starting assumption that this linear combination goes to 0, alpha k plus 1 is non-zero, that must be untrue. But then if that is untrue, that means alpha k plus 1 has to be 0. But if alpha k plus 1 is 0, then once again we are back to square one. We have a linear combination of k vectors going to 0, and by assumption with k number and the number k, the statement is true. So alpha 1 up to alpha k must also be 0. So ultimately this linear combination here must be 0. Yeah, which says that these vectors are linearly independent. Right, so there is a contradiction to this being 0, which implies alpha k plus 1 is equal to 0, but that implies alpha 1 alpha 2 dot 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 up to alpha k is equal to 0 by inductive hypothesis, which then means all the coefficients are 0. So this v1 to vk plus 1 is linearly independent, and that's what we wanted to prove. So by induction we are done. So what it says is that if there are distinct distinct eigenvalues, yeah, then if there are k distinct eigenvalues, then there will be k linearly independent eigenvectors. So of course, if there are n linearly independent, so if there are n distinct eigenvalues, so by lemma, if A has n distinct eigenvalues, then A admits n linearly independent eigenvectors. Yeah. So then so of course in that case the matrix A will be diagonalizable, right? So to understand this proof by induction better, I will urge you to do this immediate attention problem, that do the proof of the fact that if lambda 1 lambda 2 are unequal, that is they are distinct, and v1 not equal to 0, v2 not equal to 0 satisfy a v1 equals lambda v1 and a v2 equals lambda 2 v2, then v1 v2 set is linearly independent. Prove this independent of the inductive of the proof by induction. Of course, that lemma implies this immediate attention problem, but I want you to do this separately, independently. That will give you a feel of why the proof by induction is true, right? Now, once you have done this immediate attention problem, I want you to pay attention to this particular situation. You see, what I have inferred from here, that if A has n distinct eigenvalues, then there are n linearly independent eigenvectors. This property of having n distinct eigenvalues is in fact a sufficient condition, not necessary. Why do I say this? Let us look at this example of a matrix A. So this is only sufficient that A must have n distinct, remember this n is the size of the matrix A, or dimension of the vector space V. If A must have that A must have n distinct eigenvalues is only sufficient, not necessary, condition for n linearly independent eigenvectors. Why is that so? That very simple. You see, suppose I take a matrix A which looks like the following: 1 1 1 2 2. Put the zeros that you want. To make this into a legit matrix. Is this a diagonalizable? Of course it's diagonalizable, it's already diagonal. E1, E2, E3 are its eigenvectors, yeah. Does it have distinct eigenvalues? No, the matrix has size 5, so this is a 5 cross 5 matrix. So it doesn't have 5 distinct eigenvalues, it has only 2 distinct eigenvalues, but still it is diagonalizable. So this one is not necessary, this condition of uh, having distinct eigenvalues, right? Okay, but what it has is the following. You see, if I look at its characteristic polynomial, its characteristic polynomial happens to be s minus 1 the whole cube times s minus 2 square. We look at these numbers. So these numbers are called algebraic multiplicity. Multiplicities of the eigenvalues, yeah. So here eigenvalue is 1 and 2, and eigenvalue 1 has multiplicity 3, 1 has multiplicity equal to 3, and 2 has multiplicity equal to 2. These are algebraic multiplicities. Okay, and you see when you have these algebraic multiplicities, no, their sum, when you add these numbers up, that always equals the degree of the polynomial, which happens to be 5, which is the size of the matrix. So the sum of the algebraic multiplicities, sum of the algebraic multiplicities is always equal to n. This is always true. However, this matrix has a speciality. What is that? If I look at this number, dimension of the null space of the eigen, 1 times identity minus a, this is equal to 3. Indeed, you look at this 1 minus a, that is identity minus a. Identity minus a in this case is going to look like 0, 0, 0, then 1 minus 2 minus 1, 1 minus 2 minus 1. This is the matrix. What is the rank of this matrix? The rank is 2. So by rank nullity theorem, this dimension of the null space of identity minus a is indeed 3. Similarly, dimension of the null space of 2 times identity minus a, this happens to be, this will be 2 minus 1, so 1, 1, 1, then 0, 0. Yeah, this is the matrix 2i minus a. Yeah, this rank is 3, so it's its rank is 3, so dimension of kernel is 2. So you see this number matches with this number, and this number matches with this number, right? These numbers are called geometric multiplicity. So dimension of the null space corresponding to an eigenvalue lambda, this is called geometric multiplicity of the eigenvalue lambda. We'll see in the other side of this break that if for all eigenvalues algebraic multiplicity equals geometric multiplicity, then A is diagonalizable. Yeah, this is what we'll see in the other side of the break. Okay, so till then,